It was a Sunday night when Christine the baker made her famous chocolate chip cookies for the Humane Society. Follow at Chocolate Bark. They are $1 each. Talk to her if you want some. Christine always has AP chemistry on her mind and had recently learned about chemical reactions in class. It got her to thinking about what the science behind her cookies was. She did some research and learned about some of the chemical reactions that occur when you bake cookies. One chemical reaction that Christine hadn't realized was happening was caramelization. She realized her recipe said to bake her cookies at 375 degrees Fahrenheit because caramelization does not occur until 365 degrees Fahrenheit. This is when the sugar molecules break down and the cookie changes from a pasty soft beige color to a crispy dark brown, which reminded her that color changes are a signal that a chemical reaction occurred. Christine was shocked to realize how relevant chemical reactions are to her daily life.
Delicious. You may be wondering who realized chemical reactions were happening before Christine. Chemical reactions go all the way back to when Chinese and Egyptians first began studying alchemy a millennia ago. They realized that there were some type of reactions occurring when they combined two substances. However, it took until the 18th century for the science behind chemical reactions to be discovered. Carl Wilhelm Scheele first identified oxygen when studying gases, which prompted Antoine Lavoisier to measure the amount of weight gained when elements were oxidized, which he realized was due to the elements combining with the oxygen. This landmark experiment showed not only that chemistry could be a quantitative science, but that it justified the law of conservation of mass, which states that matter cannot be created or destroyed in a chemical reaction. The concept of chemical reactions involving combination of elements clearly emerged from his experiments, and his approach led others to pursue experimental chemistry as a quantitative science.
We can write out the experiment that Lavoisier did using chemical equations. Sulfur combines with oxygen, or O2, to form SO2. A chemical equation denotes reactants combining to form products through the making and breaking of chemical bonds and the rearrangement of atoms. The rearrangement of atoms happens because atoms want to gain, lose, or share electrons, become either a negative or positive ion, or to form a covalent bond, depending on which situation will provide the atom with the most stability. For a reaction to occur, there must be a lower energy configuration available to the atoms or molecules. Chemical reactions are represented by balanced chemical equations. There are full chemical equations, which show all the elements in the reaction, ionic equations, which show the ions in the full equation, and net ionic equations, which only include the ions that are involved in the chemical equation.
But chemical reactions can be tricky. Don't confuse a complex chemical reaction with a simple physical change. The chemical change is the formation of new chemical substances and involves the changing of bonds. This is shown by color change, heat content change, gas bubbles being produced, a precipitate being formed, a change in volume or conductivity, a light being emitted, a change in melting point or boiling point, or an odor created. A physical change, on the other hand, is the rearrangement of molecules, but this does not affect their internal state.
There are two main groups of chemical reactions, exothermic and endothermic. Exothermic means that the products are at a lower energy level than the reactants, or that the reaction overall releases energy, which heats up the surroundings. Endothermic reactions are the opposite. The products have more energy than the reactants, which means that the reaction requires heat and cools the surroundings. Additionally, activation energy is the energy level that the reactant molecules must overcome before a reaction can occur. A catalyst lowers the amount of activation energy needed to make the reaction occur, which speeds up the reaction. In contrast, inhibitors work the opposite way and increase the amount of activation energy needed to make the reaction occur.
There are a multitude of chemical reactions. Some of the most important are redox, double displacement, and acid-base. Redox reactions are vital to many important reactions, such as photosynthesis, respiration, and corrosion. A redox reaction is a transfer of electrons between two species. The element being reduced is gaining electrons, and the element being oxidized is losing electrons. An oxidation-reduction reaction is any chemical reaction in which the oxidation number of molecules, atoms, or ions changes by gaining or losing an electron.
Redox reactions include synthesis, decomposition, and single displacement.
A synthesis reaction or direct combination reaction is a type of chemical reaction in which two or more simple substances combine to form a more complex product. The reactants may be elements or compounds.
Decomposition is the separation of a chemical compound into elements or simpler compounds.
Single displacement occurs when a free element displaces another element from a compound to produce a different compound in a different free element. In other words, an element or ion moves out of one compound and into another.
In a double displacement reaction, the cations and anions switch between two reactants to form new products. One of the products is either a compound that will separate from the reaction mixture in some way, commonly as a solid or a gas, or as a stable covalent compound, often water. Double displacement reactions can be further classified as precipitation, gas formation, and acid-base neutralization reactions.
An acid-base neutralization reaction is a double displacement reaction of an acid and a base. But what is the difference between those two? An acid is a compound that can release hydrogen ions. Bases, on the other hand, are compounds that can neutralize acids by reacting with hydrogen ions. Some common acids you might have seen before are hydrochloric acid or sulfuric acid. Some common bases are sodium hydroxide or potassium hydroxide. Normally, in an acid-base reaction, an acid reacts with a base to form water and a salt. Neutralization reactions occur because of the formation of the very stable covalent water molecule H2O from hydrogen and hydroxide ions.
Now let's do a fun acid-base demo with an AP Chemo Lab.
Hey, so let's take a look at some of these chemical reactions we've talked so much about. In this bottle right here, we have baking powder, which acts as a base and is used in a lot of your baking needs to make things puff and produce that kind of that bready, airy flavor in cakes and cookies and stuff like that. Here is vinegar, which we commonly use in our salad or when we're cooking in various reasons, and it is a acid. So hopefully, if everything goes correctly, when we react this with this, they will neutralize each other and form a chemical reaction. The end result is this foamy mixture with a lot of bubbles in it if you want to take a look closely. And that's what science does.
A precipitation reaction forms an insoluble salt. It occurs when two solutions containing soluble salts are combined. The insoluble salt that falls out of the solution is known as a precipitate. Remember on February 22nd at 8:07 a.m. when Mr. Shannon Sue showed us this fantastic chart? The precipitate that formed can be predicted using this, or sometimes with solubility rules.
We completed a chemical reaction to form rock candy. First, we began with a supersaturated solution, which we got from first heating a saturated sugar solution and then allowing it to cool. A supersaturated solution is unstable, so the sugar will come out of the solution, forming what is called a precipitate. This method is called precipitation. The string provides a surface on which crystals will grow. As water evaporates from the string, small crystals of sugar will encrust the string. The chemical reactions of evaporation and precipitation contribute to the growth of these crystals.
Thanks to chemical reactions, we have the opportunity to complete everyday tasks like baking cookies, watering your mother's vegetable garden, or even drinking coffee so you can stay up all night studying chemistry. Yay! So next time you buy a cookie from Christine for $1 to support the Humane Society, you can think of all the chemical reactions that occurred to make it happen.